mode? You guys.
Yeah.
Not to ignore the mode, but let's go ahead and ignore it. So, what do you think? Median or average? What do you think? Median or mean, I guess. Mean. Go with mean. Okay, I'll let this idea. So rather than have you guys continually rolling dice, which was fun, but it also was time consuming, can we get the average from that distribution over there, friends? Can we get the average from that distribution over there? Think back now. Think back. Don't think present. Think back. I'm asking you a statistical question. Look at the first two words in that sentence. On average, what do you roll? Can we get an average from this distribution? Let's swing over here. The hint I want to lean towards is this right here. When this was an X and this was an F, could you find an average? How? Yes, you're absolutely correct. How do we find an average? Can you help me out?
Division is how many times you would count up how many.
Yes. So you remember what we did back in the day? We take the X and multiply it by the F, and then we basically created a new column called X times F. Now I'm not going to call X times F. I'm going to call X times P of X. I'm going to use our new language. X times P of X. And I want to talk about this. What's about to happen right now is extraordinarily subtle, extraordinarily succinct, and wicked important. Sorry to say wicked. Sorry, I was a child of the 80s. 1 times a sixth is 1/6. 2 times a sixth is 2/6. 3, you see the pattern here. Yeah. Oops, jumping the gun here. 4 times a sixth, 6. 5 times 6. 6. Now, I want to focus on what those mean. But before I focus on what they mean, I don't want to stop in the middle of what we were just doing. Is it okay, friends, can I erase this orange and blue over here? Have you had sufficient time to kind of take that in? Okay, I'm just going to feel a little more space for us. I want to go back over that side board momentarily. It's a terrible eraser. I apologize. Using Tammy's idea from before, the old average was found, X bar was found by summing up the X times F and then dividing by the total F. Remember that from the rest of the day?
Yeah.
Remember that? So you added the X times F column, and then you would add up the F column, and you divide. And essentially, we agreed about 3 weeks ago, this was the same thing as counting up all the data, because the law of large numbers kicked in. We analyzed your number of keys you were carrying on day 2 different ways. One by raw data, and one by grouped data, and the average came out to be within 0.5 of a key of each other. So, what I want to do is I want to draw the analogy between these older symbols from a random sample drawn statistically to our new probability distribution right here. So here's an intermediate step. The average of our distribution is going to be, let's use the same symbols, the correlating symbols over here. Sum of X times F is going to be the same as sum of X times P of X. And sum of F, well, F is the same as P of X, so that's going to be the sum of P of X. But you're sitting there going, wait a minute, Rule, you just told me something very special about that denominator. That denominator, sum of P of X, that always equals something, doesn't it? That always equals 1. So, and this will always equal 1, so you really don't even have to concern yourself with it. All you've got to do is add up the X times P of X column, and that will give you your average. That gives you the average. Now, at this point, you're going, I believe you, because I trust you, because I've sat in here for 5 weeks, and you've never lied to me that I know of in 5 weeks. And I appreciate that. What I want to do now is I want you to understand exactly what the hell that means by going over to the sideboard with those very numbers. So we've just mathematically, statistically connected the old formula for an average, which I think we all still buy, right? We all still buy the XF over Fs. I think we by that, right? It makes perfect sense. You're adding up all the data you've got, dividing it by how many data points there are. Same thing's happening here, Chessa. Go.
But it doesn't really matter because this isn't quantitative data?
It is quantitative data. The number of dots on each side of the die. That is quantitative.
But I mean, you could replace it with shapes just as easily. And
Oh, you could. That would be qualitative data, but because it actually has numbers on the side, I can ask on average, what number do I get? And 2 is twice as big as 1. 3 is 3 times as big as 1. I love what you're saying. Just drawing the connection between this and Likert scale data. Thank you. This is perfect. But this actually is numerical data. It actually is numerical data. You're 100% correct. You're 100% correct in saying I could replace those with shapes. But the thing is that think about when you use dice. Like, for example, board game. You roll a die to tell your piece how many spaces to move. So it actually does have a numerical underpinning. Of course you're correct. If we replaced it with shapes, this argument will go out the window. Completely. You can't average a heart and a spade, but you can average a 1, 2, 3, 4, 5, and 6. Love that, Jessica. Thank you. That was perfect. That was perfect. Cool?
Yeah.
Great point. Great point. You sure you can miss? I want to make sure you're not just saying that just to...
No, I get it.
It's all about context. If you're using the die to stand for something numerical, then it's quantitative. But if you're replacing it with qualitative data, then we have to talk about modes. Very good, my friend. Now, back over to here. I think we now agree that the average of this distribution is just adding up those xp of x's. So, I got a 1/6 plus a 2/6 plus a 3/6 plus a 4/6 plus a 5/6 plus a 6/6. And Chester, this actually inadvertently helps answer your question even further. What I want to look at is what each of these 6 numbers means. The first 1/6 was the product, as you remember, of the value of the die and the frequency of occurrence of that value. So 1/6 of the time, you get a 1. So on average, you get this much towards the average from the ones. On average, over time, 1/6 of the average comes from the ones, because there's only 1 dot on that side. Likewise, you get this much. Can I use quotes going sideways? If I do this, you get this much towards the average from the 2s. This isn't exactly, it's kind of breaking the definition of how to use quote marks. So you get 1/3 or 2/6. You get twice as much stuff from the 2s just because 2 is twice as big as 1. So it's going to give us twice as much stuff on average over time. This is only because it's quantitative data, my friend. Only because it's quantitative data, not because it's a shape or a color or anything like that. But you get twice as much stuff. You get 3 times as much stuff. You get this much stuff towards the average when you roll 3s. You get this much stuff from the 4s and the 5s and the 6s. So what you end up doing is you add up all the components of the average in the same way you added up the number of people who had between 0 and 2 keys, the number of people that had between 3 and 5 keys, the number of people that had between 6 and 8 keys, the number of people that had between whatever the next one is, 9 and 11 keys. It's the same thing, except we're talking about the size of the die right now. It's exactly the same thing. There's no difference in the argument, except for the fact that I don't have the actual number of people that rolled 1s and 2s and 3s, but I know what happened 1/6 of the time. So 1/6 of the time when I roll the 1s, I'm going to contribute that much towards the average. What does this all add up to be, friends? What do we get here? 3, 6, 10, 21 over 6? Which is what? 3.5. Which is exactly the same number we'd get if we did the median, wouldn't we? If we did the cha-cha-cha-cha-cha. Yeah. Because we go cha-cha-cha-cha-cha-cha. All the 1s and the 6s would go away. All the 2s and the 5s would go away. And then we cha-cha-cha-cha-cha. And all the 3s and the 4s would go away, which means we were directly in the middle, which is 3.5. So on average, you're going to roll a 3.5. How the hell can you roll a 3.5? You can't. But you can what a 3.5? Starts with an A. We've said it about 3 dozen times now. You can average 3.5. Here's why. For every 6 that gets rolled, what gets rolled somewhere else? A 1, which averages to 3.5. For every 5 that gets rolled, what gets rolled somewhere else? A 2, which averages to 3.5. For every 4 that gets rolled, what gets rolled somewhere else? 3, which averages to 3.5. And remember, it doesn't happen uniformly. As the thing approved an hour and a half ago, you said it is not a promise, but it is a long-run average, and that's why it averages to 3.5. Fair enough? That's the big idea. That's the big idea. And we're going to drive this point home, I promise you, over the next 5 weeks together. There is no difference between what we just did here and the averages you took 3 weeks ago. Zero difference. There is no difference whatsoever. Can I answer that question?
Oh, no.
Oh, okay, I saw motion. Like an activity, I see motion. And there-ish. Now, you can crank this in your TI, and I highly encourage you to, because there's also a standard deviation that goes with this bad boy. Don't worry about that right now. I do want you to get used to this, though. The average was 3.5 pips on each roll of the die on average. And it's the average. You can go ahead and call that average mu now. Remember mu? Remember mu? Who the hell is mu? Who is mu? Greek letter for M. Do you remember we mentioned him many weeks ago, i.e. about 3 weeks ago, and I said, don't worry about this guy right now. We're going to deal with him more later on when he's more practical. So what average have we been talking about nonstop since the beginning? What do we call the average? What does your TI call the average? The mean, which symbol-wise is X bar. And what is X bar? The average of the average of a sample. It's a sample average, correct? What's mu? It's the average of the entire population. How can I sit up here and tell you that we can call this mu? Why don't I have to call this X bar? Look back up here. How can I call this mu? How can I call this mu? Friends, what exists in that distribution right there? Beth, a little bit louder, please, my friends, so I can let that wash over me.
An entire population.
It's 100%.
A little bit louder.
It's 100%.
100% of the time, the results you get from the experiment are going to fall in this distribution. Therefore, it's not a sample. It is an honest-to-goodness population average of what has to happen on average. It is, honest-to-goodness, a population measure. So you can call it mu. And what you'll see next time is when you run the standard deviation, on these bad boys, there is no sample standard deviation. You know how there was 2 standard deviations in your TI? There was S and little sigma. S goes away. There is no sample. It's an entire population. This stuff's amazing. This governs insurance rates. This governs what you pay for your cell phone. I mean, more on that on Wednesday as well. But can we take a few moments right now? Ask me any questions you've got right now about. We filled the board with a bunch of stuff today. Is any of this not sitting okay with you right now? Chestnut, thank you so much for that bit about the numerical versus quantitative. That was fantastic. Hopefully I put your mind somewhat at ease. You don't look 100% convinced yet, but that's okay. Well, I promise you we'll get to you. Any questions popping up right now? I want to roll dice a little bit more to collect some more data for next time, but as far as questions on this first, anything coming to mind? Are you kind of like, okay, I'm rolling with it right now. I'm not exactly sure how I should feel right now. Still kind of hungry. Another cup of coffee would help, that kind of thing. Yeah. Okay. This, do you remember what kind of distribution I said this was? It starts with a U. Remember the phrase that because all these were the same? Oh, it's actually how would you? It's like uber modal because everything's equally likely. That's okay. Uniform, and don't memorize this. Please don't memorize this. It's uniform because all the probabilities are the same. What I want to do right now is I want to generate one that is, Tammy, say it again, unimodal, but still symmetric. This is symmetric and uniform. That's kind of redundant. You'll see why later. I want to generate one that's symmetric and unimodal, not multimodal. So here's what I want you guys to do next. You got 2 dice, correct? I want you to roll them as a pair. Let's do it 20 times. That'll give us a good chunk of data. 20 times and write down the sums that you get each time. The sums. So if you roll a 1 and a 4, write down a 5. If you roll a 6 and a 5, write down an 11. That was a 1 there. Good. You want to use that one? By all means, if you want to. I'm going to shut this down while we do this.